Hello, welcome to the fourth week of Recitation for EE2423 Network Theory class. Today I will be solving some problems, and the main focus of this recitation is to show you how to use node voltage and mesh current techniques to solve some simple circuits. Alright, right now I have the first problem, and as you can see that we have a quite difficult circuit here. So we have two current sources, we have four resistors, and if you notice, I have written these voltages V1, V2, and the current I1. And the question here is the first question. So A, what are the values for V1, V2, and I1? B, so the next question is power delivered or produced by the current source, not the voltage source. Current sources, because you have two current sources. All right, now to solve this problem, you can use either node voltage or mesh current techniques. I believe you already studied that in the class with Dr. Alamaniotis. But for this specific problem, let's use the node voltage technique. So to use the node voltage technique, then we need to identify essential nodes, right? So essential nodes are nodes that, so a node that is connecting three or more uh, units. For example, we can see that this is one essential node because it connects the one current source and three resistors, right? And this thing, though you can say it's node, but this node is essentially the same as this one. So because you can always redraw something like this, right? So they are the same actually. This one is 15 ohm. So you have one essential node there, and the other is obviously here. So we have two essential nodes. So that's why when we are using the node voltage technique, then for this case we will have two equations associated with the two essential nodes. All right, and if you also look closely, then for each node, say node 1, node 2, then we already label the voltage at node 1 as V1 and the voltage at node 2 as V2. All right, so and the current flowing from node 1 through node 2 by the 5 ohm resistor is I1. All right, okay, so let's apply the node voltage technique at node 1. What do we have? Sorry about that. Node 1, we have, so first the current from this source is going into the node, right? But the node voltage technique is defined for assuming that current is going out from the corresponding node. So we have minus 15, right, plus the current going out from that node going through this branch. So we have the current going out here is V1 over 60, right? Because we are assuming that this is just zero or ground, it's connected to a ground, plus again the same V1 over 15 plus the current going out there. Why is the current going out there, which is I1, right? So you can write I1, but you can expand and write I1 as V1 minus V2 over the resistance there, which is 5 ohm, and that should be equal to 0, right? So that's the first equation. And yes, you can simplify it, so let's do that. 1 over 60 plus 1 over, sorry, this is 60, 15 plus 1 over 5 V1 minus 1 over 5 V2 is 15. Okay, so can you simplify it further? So let's multiply both sides with 60. So we get 1 plus 4 plus 12 V1 minus 12 V2 equals 15 times 60, which is 900. So this is 17 V1 minus 12 V2 equals 900, and let's call it equation number 1 at node 2. So the equation at node 2 is the same thing, so it should be minus I1, right? Because we are assuming that the current is going out from the node 2, so we have minus I1. But since this is I1, then minus I1 is the opposite of this, right? So you put negative sign, so you have V2 minus V1 over 5 plus current going through this branch is V2 over 2, and then the current from this current source, and the direction is going out from the second node, so we have plus 5 there. Okay, again let's simplify it. We have minus 1 over 5 V1 plus 1 over 5 plus 1 over 2 V2 is minus 5. Let us multiply both sides with 10 to simplify the equation, so we get minus 2 V1 plus 2 plus 5, right, V2 minus 50. So we have minus 2 V1 plus 7 V2 equals minus 50, and this is the second equation. So from the first and second we can write using matrix form, because essentially we want to solve the first and second equations, right? We have two equations, we have two variables V1 V2, so we want to find the value V1 and V2 that satisfy the first and second equations, right? So of course there are many methods that you can use, like substitution and anything else that you have in mind, but for these equations I will solve it using matrix. So for this method, we write the first and second equation in a matrix form. So we have 17 minus 12 minus 2, 7, v1 v2 equals 100 and minus 50, right? Okay. And we need to find the value for v1 and v2. So v1 and v2 is simply the inverse of this, 17 minus 12 minus 2, 7, inverse multiplied by 900 minus 50. Okay, and this is one method. You can also use the Gauss elimination, so you reduce the number of, so makes bunch of zeros here, so you can get v2 directly, and then once you know v2 you can copy v1. That's another method, but this method is more intuitive, right? Because if you multiply this equation with the inverse 17 minus 12 minus 2, 7 inverse, so this becomes identity matrix. So you get v1 v2 equals this matrix inverse times this vector. That's the same thing. So I believe you should know how to inverse a matrix 2 by 2, 3 by 3. You should know how to do that, so I will not show the steps to obtain the inverse matrix. I will just write the solution here. v1 v2. So once you know the inverse, you can just multiply it with this factor. We obtain 60 and 10. It means that v1 is 60-fold, v2 is 10-fold. Alright, so we know v1 is 60-fold, v2 10-fold, and what is I1? By definition, I1 is here, right? You know, I1 is v1 minus v2 over 5, so 60 minus 10 over 5, 50 over 5 is 10 amps. Okay, so these are the solutions for point A. How about the power? Okay, so the power is a little bit tricky because you have sign that you should not forget, because the sign determines whether some sources are consuming power or delivering power. Okay, so the convention is the following. So when we have something like voltage or current source or even resistor, and we define the voltage as plus minus, and the current is going out, right? If the current is going out, then the power is negative, so power is minus VI. It means that this system is delivering power. But if the current is going in, then the power is VI, meaning that this unit here is consuming power or dissipating power. Alright, so this for A. For B, so look at this 15 amp current source plus minus, and the current is going out, right? The current is going out from this source, so we are using this equation. P at 15 amp is minus the voltage. The voltage is V1, right? V1 is 60, so 60 times the current 15 is minus 900 watts. And look closely on the question. The question is how much power is delivered by the current sources. So is the current delivered minus 900 watts or 900 watts? Okay, so this convention is for passive convention. So passive means it assumes that we are consuming power. So this power minus 900 watts is equivalent to saying that this current source is consuming minus 900 watts, which is equivalent to it delivers 900 watts. Okay, so consuming minus 900 is equals to delivering 900 watts. How about the power at 5 amp? So look at the voltage sign, plus minus, and the current is going in, so we have this, right? So V is VI, so what is V10 times 5, 50 watts. So actually this current source is consuming 50 watts, thereby it delivers minus 50 watts. Okay, so don't get confused by this power thing, alright, because you should be able to tell whether one current or voltage source is consuming or delivering power, and always answer based on the question. If the question is how much power is being delivered by a current or voltage source, then you have to state how much it's delivering. Okay, all right. So that's the first problem. Let's go to the second problem. We have voltage source 80 volt, resistor 30 ohm, 5 ohm, 90. I need more space, so 50 ohm, sorry, it's 5, 90 ohm, 26 ohm, 8 ohm. Okay, the question is power delivered by the 80 volt source and power dissipated by the 8 ohm resistor. Okay, and for this particular problem, it is specified that we should use the mesh current technique. Okay, so that we can learn how to use different techniques to solve circuit. So in the first problem we use the node voltage technique. So in the second problem we need to use different technique, which is the mesh current. So it is similar to the KVL, Kirchhoff voltage loop. So we define three loops because we have three loops or three meshes actually. So there are differences on the division between mesh and loop. Okay, so and the technique is called the mesh current. So we need to define the meshes. The first mesh, so I will not call it loop, then it is the first one. The first mesh, the current is I1. I prefer to use capital I, so I1. This is I2, I3. Again, I use clockwise direction to define the meshes, but again you can use different directions. Maybe you want this, only the second loop is counterclockwise. It doesn't matter as long as you are consistent with your definition, then you should be fine. But for simplicity, usually we define the direction of the meshes clockwise, or so all meshes are clockwise or all meshes are counterclockwise, just for simplicity. All right. Okay, let's write the equation. The first mesh we have minus 80 plus 5 I1, but 5 I1 minus I2, right? Plus 26 I1 minus I3 equals 0, right? So we can simplify this equation. It's 31 I1, sorry, 31 I1 minus 5 I2 minus 26 I3 equals 80. Second mesh, we have, okay, let's start from here. 5 I2 minus I1 plus, here is 30 I2 plus 90 I2 minus I3 equals 0. And by simplification, it is equal to minus 5 I1 plus 1 to 5 I2 minus 90 I3 equals 0. Okay, the last one we have 26 I3 minus I1 plus 90 I3 minus I2 plus 8 I3 equals 0. By simplification, we obtain minus 26 I1 minus 90 I2 plus 1 to 4 I3 equals 0. Alright, we have three equations. Let's call it number 1, number 2, number 3. We have three equations, we have three variables, so we should be able to solve this linear equation. Again, I prefer to use matrix, so let's write in a matrix form. 31 minus 5 minus 26 minus 5 125 minus 90 minus 26 minus 90 124 I1, I2, I3 equals 80, 0, 0. Again, so they are equivalent. I1, I2, I3 is nothing but 31. So this matrix inverse multiplied by this factor 80, 0, 0. Okay, again, you should be able to compute the inverse of 3 by 3 matrix and from the linear algebra class that you took. So blah blah blah, you compute this, we get 5 to 2.5. Okay, it means that I1 is 5m, sorry, I2 is 2m, I3 is 2.5. Okay, now we go back and look at the questions. The first question is, how much power is delivered by the 80-volt voltage source? Okay, we know that I1 is going to that direction, right? So it's going out. So we are using this equation. P is minus Vi. So this is A. Oh, sorry, this is A. P at 80 volt is minus 80 volt times I1 5, right? So 80 times 5 is 400 minus 400 watts. Okay, why minus? So it means that the power consumed by the 80 volt voltage source is minus 400 watts, which is equivalent to 400 watts of power being delivered. Alright, B, power consumed or dissipated by the 8 ohm. So P at 8 ohm is I3 times I3 squared, right? I squared R. So R, so we know I3 is 2.5, so 2.5 squared times 8, right? And 8 is equal to 50 watt. So 50 watt of power is consumed or dissipated. Okay, that's the second problem. Last problem, number 3. So in the first and the second problems, we have been using the node voltage and the mass current techniques. For this problem, particularly problem number 3, we're not allowed to use the node voltage or the mass current techniques. Okay, so let me draw the circuit first. $40 ohms, 20 ohms, 70 ohms, 30 ohms, 50 ohms, and then 10 ohms. All right, and okay, so the labels are, we have V1, so the voltage plus minus voltage at the 80 ohm resistor is V1. Current at 30 ohm resistor is, let's say, I1, and the voltage at the 10 ohm is V2. The question is find V1, V2, I1. Without using the voltage, not the not voltage technique or the mesh current technique. So here we will be exploring different techniques to solve this circuit, and the new technique, different from the not voltage or the mesh current, is the voltage division and current division. So what are those? So you should have learned these techniques, but I will explain it again briefly, how to use the voltage division or current division. All right, okay, first is voltage division because it is more intuitive to work. All right, let's say you have two resistors. Let's write resistor R1, R2. They are in series, and the total voltage is V, and the current, the total current is I. Okay, and we have the voltage of each resistor is V1 for R1 and V2 for R2. So the question is, what is the relation between V1 and the total voltage, and the same, what is the relation between V2 with the total voltage V. Alright, we know that V, so the total voltage V is I, total current, times the total resistance, right? R total, right? We know the current at R1 is the same with I because we only have one branch, so they should have the same current, right? So I is also V1 over R1. I is also V2 over R2. So from here we have I is V over the total resistance, which is R1 plus R2. Okay, since this current is the same as this one or even this one, then we can have V1 over R1 is V over R1 plus R2. So V1 is R1 over R1 plus R2 times V. The same thing with here, so we get V2 is R2 over R1 plus R2 times the total voltage. Okay, so from this and this equation, so from these two equations we can deduce that the voltage on R1 is proportional with the resistance. So if R1 is bigger than R2, then V1 must also be bigger than V2. Okay, so this is called a voltage division. How about current division? We have current. So for current division, we have two resistors R1 R2 in parallel, right? Plus minus, again they have the same voltage and also the same current. Let us assume that the current flowing through R1 is sorry, this will be the capital, just capital I. This is I1, this is I2. Okay, the same. So V voltage is, the total voltage is equals to the total current times the total resistance, right, which is R total. Again, since these resistors are in parallel, then we know that V is also what is also I1 R1, V is also I2 R2. So we have what here? We have V is I times the total resistance, right, with R1 parallel with R2. Alright, so we have this V, this voltage is the same as this one, so I1 R1 is I R1 parallel R2, but R1 parallel R2 is what? Is R1 R2 over R1 plus R2. Therefore, what is I1? I1 is R2 over R1 plus R2 times the total current. The same thing with here. You can show that I2 is R1 over R1 plus R2 multiplied by I. Okay, so look, notice that this equation, so I1 is R2 over the total resistance multiplied by the total current. So the current flowing through R1, if R1 is bigger than R2, meaning that R1 has more resistance than R2, then the current flowing through R1 should be less than the current flowing through R2, right? Because R1 has greater resistance. Greater resistance equals less current, right? Because that's the definition of resistance. You have more resistance, the current will be less. The lower the resistance, you have more current flowing. So if R1 is greater than R2, then the current on R2 must be bigger than R1. That's why for current division, these are opposite, right? The voltage and the current division are opposite. Okay, so that should make sense. Let me know if you have questions. So we'll be using this voltage division and current division to solve this circuit. So how to find V1, V2 and I1? So the idea here, we need to find what is the total current. Why is the total current going here? Say I. Why is the total current there? So the idea here is we need to simplify this series and parallel connections of resistors into, so we need to break this into one single voltage source, one single resistor, which is we do not know, And if we know the resistance, the total resistance, we can compute the current I, right? We need to simplify. We need to simplify this circuit. Okay, so let's do it. The first step is, first look at here. We know that the 50 ohm and 10 ohms, they are in series, right? So you have two resistors in series, then the total resistance uh, is added, right? So 50 plus 10, right? So we have, you can replace it with one single resistor, 60 ohm resistor, right? Because 50 plus 10 is 60. All right, so we have 60. Just keep that in mind. So you have 60, and it is parallel with 30 and also 20. So we have 20 parallel 30 parallel 60, right? So if it is too difficult, then let's do it one by one. So you have 60 parallel with 30, so 60 parallel 30 equals 30 times 60 over 30 plus 60, right? Okay, 30 60 over 90, we have cancel 1 3, cancel 1 2, 3 times 2, you have 20 ohm. So these three resistors is equal to 20 ohm, and 20 ohm resistor is parallel with 20, so you get half of the resistance, 10. So you have 10. So the total resistance is 40 plus 10 plus 70, right? Which is R is 120 ohms. So I is 60 over 120 is 0.5 amp. Okay, we know I. So what is V1? V1 is 40 times 0.5, right? V is resistance times current. 40 times 0.5 is 20 volt. That's your V1. Okay, next, the current flowing through this, say this, is also I, right? So it's still 0.5 amps. So let's use the current division here to compute I1. So I1, what is I1 here? So I1 is 20 parallel with 30 parallel with 60 over 30 times the total current, right? So why it is different with this? Because I'm keeping this, so you have I1 times 30, because we have 30, right? 30 ohms there. So I1 times 30 equals to I, which is 0.5, multiplied by the total resistance, right? Which is 20 parallel 30 parallel 60. So I1 is 20 parallel 30 parallel with 60 over 30 times 0.5. So you can compute this. It is equal to 1.167 amps. That's I1. Okay, we know I1. The last question here is, what is V2? To compute V2, we need to compute the voltage at this 30 ohm resistor. So V at 30 ohm is 30 times 0.167, right, which is 5 volt. Okay, we know that the voltage here is 5 volt. To find V2, we need to apply the voltage division. So V2 is simply 10 ohms over 5 plus 10, which is 60. 5 plus 10 times total voltage there, which is 5. So 10 over 60 times 5, right, which is 0.833 volt. Okay, so these are the answers. All right. Okay, so if you still have any question, you can email me or come to my office hour. Okay, so that's the end of this recitation class. I'll see you next time. Goodbye.